Okay, we're going to be looking at example 3-7, again from the latest version of Shigley, also included in my notes. And what we're looking at is the effect of transverse shear, VQ over IB. And so we have a beam that is 12 inches long. It has a given cross-section dimensions as given. It is simply supported, and it has a load that is offset from the center. And we were asked to calculate the stresses. Let's see, let's read the words exactly. It says, basing the design only on the bending stress, a designer has selected this 3-inch aluminum channel with the cross-sectional dimensions shown. If the direct shear is neglected, the stress in the beam may be if the direct shear is neglected, the stress in the beam may be higher than the designer thinks. Determine the principal stresses considering bending and direct shear and compare to just the bending. Okay, and so of course we're going to need a moment of inertia, those kinds of things. And so we are given in the problem statement that I is equal to 1.66 times 1.66 inches to the fourth. That's been pre-computed for us. And we do have a symmetric cross-section, so top and bottom C values are the same. And so C would be the 1.5 dimension, and I over C is 1.1 inches cubed, and that would be the section modulus. Then taking the 488 pound load and doing the statics, which we're skipping here, we get, of course, since the load is to the left, we get a much higher reaction to the left, 366 and 122 here. And if we draw the shear and moment diagrams, we have a 366 up, constant and over, and then 488 down and over, and then up 122. And then because we have a rectangular shear, we then have a triangular shape for the moment, with the moment peaking at this distance of how far? 3 inches times the 366, giving us a 1098 peak inch-pound force moment. And so we are going to operate this thing at the peak moment. And we will take into account what's happening because on the left-hand side, this peak shear of 366 at the same point as the peak moment. And so here's what we want to do. We presume that if we only paid attention to bending stresses, then MC over I, where C is the largest, 1.5 inches to the top or to the bottom from the neutral axis, MC over I would be our stress that we have to deal with. And it acts alone because there is no transverse shear at the top or bottom of the beam. But because of the kind of shape that we have, the transverse shear in the skinny section, right as it's about to enter the wider section, that transverse shear might be fairly large. And because we haven't moved very far from the top of the beam, the MC over I, because C is still pretty big, or the MY over I, because Y is still pretty big, might actually give us a worst case stress. So we need to calculate MY over I at this corner, and we need to calculate VQ over IB at this corner, and take them to Mohr circle, combine them, and then compare those stresses to the pure bending stresses that would occur at the top and bottom fibers. So that's the plan. Looks like I, on the next page, repeated the shear and moment diagram so that we could do a sigma is plus or minus MC over I. The max moment was 1098, C was 1.5 inches, I was 1.66, and we get a plus or minus 992 psi at the top fiber and at the bottom fiber. The question is the total stress at this corner, because of the added VQ over IB, is the total stress worse there? Let's go find out. We can calculate the bending stress MY over I at our point of interest, noting that Y is 1.227. We calculate that bending stress and we get an 812, and because of the nature of the moment, it would be compressive up at that top section, so 812. Now we need to do a VQ over IB. V we'll get from the shear diagram. I we already have. B will be the thickness of the part right here. I'll have to go look that number up. I don't see it right here, but they'll give it to us. And the Q is the area above our cut line times the y bar as measured from the neutral axis, the location of y bar above the cut line. So let's look at how Q is calculated. So Q is equal to the y bar first, which is 1.227 to the bottom of the surface, plus half of this upper distance, 1.227 plus 0.273 divided by 2. That would be the y bar piece measured from the neutral axis. Then the area would be the total thickness, 0.273, times the total width, 1.41, and then multiply all this together, and we get a Q value of 0.525 inches cubed. V was 366, I is 1.66, and B at that location is 1.7. Now I put a note on there that says Y 1.7. That's the thickness of this thin region, not the thickness of the wide region. Q, there's a step change in Q. I'm sorry, there's a step change in B. B is skinny until we hit right here, and then B jumps up a lot. Well, we would like that, we want the shear stress at its highest, at its worst case, and so we're going to use a small value of B, which was the, what, 0.17 or so, 0.17. So, VQ over IB, 366, 0.525, 1.66, and 0.17 is a negative 681 psi. Doesn't seem all that large, but if you go back and look at the bending stresses, that is actually pretty large as compared to those bending stresses. And so now we need to take the 812 and the 681 and combine them in a Mohr's circle and see what we learned. And the sigma 1 and sigma 2, the two principal stresses from the Mohr's circle, would be the center plus the radius. Plugging in the numbers, we get that sigma 1 and sigma 2 with the plus or minus sign here would be a positive 387 or a negative 1200 psi. That negative 1200 psi is significantly bigger than the MC over I only at the top and bottom fibers. Matter of fact, it is 21% bigger than just bending alone. And so it is possible that this beam might fail. We don't know because we weren't given strength information. But if it were sized to carry the 992, and if it just barely makes it, then this might in fact be a failure stress, which says be careful. Now, in this case, why did VQ over IB matter? I think it probably mattered for a couple of reasons. First of all, we have a very short beam. Okay, so the bending moments were very small, which made the VQ over IB fairly large in comparison to the bending moments. So we got a very short beam where Q could be significant. And the other is that we did have a very skinny cross-section that abruptly changed very near the top, which allowed our large VQ over IB allowed VQ over IB to be fairly large at a fairly far distance from the neutral axis, where it combined with a fairly large bending stress. So put those two together and we might have danger. You have to check it.